Determine the total resistance of the complex circuit shown below. Now we're delving into more complex resistor combinations that involve both resistors in series and resistors in parallel. And just for a quick reminder, resistors in series would look like this, where resistors are joined end to end, where there are no branches in the circuit. And resistors in parallel would look something like this, where we have resistors on separate branches within the circuit. So on the surface, this problem looks really difficult to do, but we can simplify this problem by dividing this circuit up into groups of either parallel or series resistors. And we'll see how we can do this as we move ahead in the video. So let's start off by redrawing this circuit so it now stretches along a line, where the positive terminal is now on the left-hand side, and we've marked that with a positive 9 volts, and the negative terminal, or sometimes called the ground, is on the right-hand side. The only reason we're representing the circuit like this is to make it easier to see how this circuit is structured and what resistors are connected in series and which resistors are connected in parallel. Now, there are two formulas we need to use in the next couple of steps, and I did cover these in more detail in the previous two lessons, which I'll link up in the card above. The first one of these formulas shows us how to calculate the total or equivalent resistance of a sequence of resistors attached in series. In other words, attached end to end with no branches in the circuit. The second equation tells us how to calculate the total or equivalent resistance of a set of resistors connected in parallel. So now, with our complex circuit above, we are going to locate sections of the circuit that have resistors in series and calculate their equivalent resistance, and then we'll focus on resistors in parallel. So in our complex circuit, I can spot two sections where we have resistors connected in series. Can you spot these two sections yourself? On the left-hand side, we have a 3 ohm resistor and a 6 ohm resistor in series, which I've labelled Group A. We also have a 6 ohm resistor and a 2 ohm resistor attached in series at the top here, which I've labelled B. We can use our formula for resistors in series to find their equivalent resistances and then redraw our complex circuit with these new resistance values. And this is the first step in simplifying this complex circuit. So the equivalent resistance or total resistance of Group A is the sum of these two resistors. 3 plus 6 equals 9 ohms. And for B, we have 6 plus 2 ohms, which is 8 ohms. So now we can replace Group A and Group B with single resistors of values 9 ohms and 8 ohms respectively. And these are the equivalent resistances of those series resistors, with those resistors connected in series. Now we can work on the resistors in parallel and find their equivalent resistance using the parallel equation for resistance. So what values do you think we should place into the variables R1 and R2 in our equation here? Remember, this equation is only for resistors that are connected in parallel. Well, it doesn't matter which way round you do this, but you would place the 4 ohm or the 8 ohm into these fractions. And when we sum this up together, we get a total of 0.375 ohms to the power of -1. So in order to get the total resistance value, or the equivalent resistance, when our equation looks like this, what we have to do is isolate the total resistance value. And we do this by dividing both sides of the equation by 0.375 and multiplying both sides of the equation by the total resistance. So you see here on the left hand side that the total resistance symbol here cancels out, and on the right hand side our 0.375 cancels out. This leaves us with the equation of the total resistance is equal to 1 divided by 0.375. So our total resistance comes to 2.6 ohms reoccurring. And the period on top of the 6 simply means that this number repeats forever. So now we can replace this parallel section with this equivalent resistance. This leaves our circuit looking like this, where we have 3 resistors in series. What's the last thing we need to do to find the total or equivalent resistance for these 3 resistors in series? We simply use our series equation again and add the resistances together. This gives us a value of 12.6 recurring ohms, which it can round up to 12.7. And this answers our original question. This is our total resistance of our complex circuit. Now we could go a bit further here and try and work out the circuit's total current, given the fact that the circuit is powered by a 9-volt battery and has a total resistance of 12.7 ohms. So how can we do this? How can we calculate the circuit's total current? Well, we can use Ohm's law, which is delta V is equal to the current multiplied by the resistance, and rearrange this equation to make the current the subject of the equation. So I've divided both sides of the equation by the resistance, which isolates the current. So 9.0 volts divided by 12.7 ohms is equal to 0.71 amps to 2 significant figures.